seminar work about the mechanical strength and fracture resistance of resistant weather spots obtained between advanced high-strength steels. In particular, here we will see the results coming from the resistance spot welding between quenching partitioning steels and strip steels. This is a preliminary study in collaboration with some colleagues of Polytechnic. In particular, the steel grades that are used for the fabrication of car body components need to fulfill some requirements. In particular, the main requirements are high strength in order to produce low weight car body components, and so to obtain lower fuel consumption, less pollution, increased load, and lower cost. As well as these steels need to have a high plastic energy assumption in order to guarantee car crash safety, fatigue and endurance, formability, because generally these steels are formed in order to obtain the final component, and weldability, because these steels, in particular their components, are generally assembled together by using welding technique. So in the last decades, advanced high-strength steels are increasingly used in the fabrication of car body components. This is a picture that briefly summarizes which are the steels that are currently used in the fabrication of car body components. In particular, here we have the conventional steels, such as interstitial-free steels, the carbon steels, and so forth. Then we have strip and dual-phase steel, complex steel, martensitic and hot stamping boron steels that are generally used for the fabrication of these components. Today, some components are also produced by using twinning induced plasticity steels. And then we have to consider that other steels are under research and development. In particular, the tendency in the last year is to produce new steels that are located in this graph in vision, particularly by producing thick steels with low amount of manganese due to the problem coming from fabrication process of these steels, or to produce strip by nifty steels, or another feature that can be followed is to fabricate quenching and partitioning steels and use these steels for the fabrication of these components. In particular, the widespread usage of quenching and partitioning steels is also conditional on their aptitude to be welded with other steels. And so, for this reason, we have carried out this preliminary study in order to understand better which are the mechanical properties of the resistant welder spots obtained by welding these new advanced high-strength steels, represented by quenching partitioning steels, and strip steel grade. In particular, here you can see a comparison between steelwork heat treatments that are generally used for the fabrication of these steels. In particular, on the left side, you can see fabrication processes for the quenching partitioning steels. As you can see, initial austenitic heat treatment, rapid quenching at the temperature between martensitic start and martensitic finish, and maintaining at this temperature for a certain given time in order to allow the carbon present between the martensite to go inside the austenite to promote this movement of atom carbons. We need to increase a little bit the temperature of the steels, and then we have a final quenching in order to obtain a final microstructure that generally consists of retened austenite and martensite. However, in some cases we can also have some amount of manganite and ferrite in these peculiar steels. And here you can see instead the conventional steelwork treatments that are used for the fabrication of steels. In the first case, in order to obtain a polygonal ferrite matrix, or in this other case, to obtain a magnetic ferrite matrix. Here in particular, you can see chemical composition of the two examined steels. As you can see, these steels are mainly carbon manganese silicon steels. The main difference is due to the steelwork treatment that you see, that you saw before. And here you can see also the main mechanical properties of the steels: hardness, liquid hardness, the yield strength to steel, the ultimate tensile strength, and the elongation strength. And here you can see in better detail which is the microstructures of the two examined steels, particularly the quench and partition steels. As said before, we have martensite and austenite. Instead, in the microstructures of the steel, we have a ferrite, which is a matrix, some part 2 by 9 faces, and then we have some austenite iron. We have carried out a resistant welding test by using an industrial medium frequency AC machine. Particularly here you can see the main important characteristics of this machine represented by this 120 kW capacity. We used two Cronin level copper electrodes with the electrode phase of 6 mm. In particular, in order to evaluate also the effect of the main important welding parameters on the final mechanical strength of the weld spots, we have applied an orthogonal array considering 9 tests with different process welding parameters, and we have carried out 4 replications in order to obtain consistent results. And so you can see that we can have this test where we have low welding current. In this other test, we have medium welding current, and in this final test, we have high welding current. And for each of this group, we have an increase of the clamping force that was used for the experimental test. So by changing the welding current, the welding force, and the welding time, we have applied this experiment. Here you can see the size of the samples that were obtained after welding test. In particular, the samples were used according to this AWS standard that it's the reference standard for an evaluation of the mechanical strength of resistance weld spots. In particular, the results obtained from this test are represented by the maximum peak load reached during the test, that consists in a traditional tensile test, and the area that you can find under the curve up to the peak load. And these are the two main important information that can be collected by this test. Here you can see in more details which are the microstructures of the two steels after the welding process. In particular, you can see in this region the weld nugget, that is the region of the steels that melted during the welding process. Then we have around the welded nugget the heat affected zone, and then we have outside this region the base materials. And so in the upper figures you can find which is the unification of the microstructures of the three steel coming from this point to the weld nugget, and similarly you can see also the microstructures variation of the quenching partitioning steels. Here you can see overview about the dimension of the weld nugget, in particular considering the diameter of this region, and the thickness of the weld spots. That are two geometrical features that are important to evaluate the quality and of this typology of welding process. In particular, obviously, we have a variation of the nugget diameter and of joint thickness according to the process parameter that were used during the test. In particular, you can denote that in the last test, we had some metal expulsions from the weld nuggets. That means that some metals go away from the nugget, and so we can have some problem related to the presence of defect in some cases, or to a reduction of mechanical strength. But particularly we can see that increasing the welding current, we have an obvious increase of the nugget diameter. However, here we have not a defining trend because we have a weld metal expansion. Instead, the joint thickness more or less does not change significantly in all the tests. In particular, here you can see that the microhardness profiles obtained in the joints in the several welding conditions, but you can have a look in the manuscript. Generally, we have an increase of hardness in the weld nugget because we have a formation of full martensite within the nugget, and then we have a reduction of the hardness coming from this region to the base material. Considering that in this region we have some tempering phenomenon of the bainite in the tube steel or the martensite in the punching steel. Here you can see instead some graphs showing you which are results obtained from the shear tension test. In particular, here you can see the mechanical strength obtained by the test as peak loads. In particular, you can see due to the nature of the welding process, we have to consider that we have quite a large scattering, but we can identify a sort of trend in these results. In particular, you can see that there is increase in the mechanical strength of these joints, considering also that coming from this position to this one, we have an increase in the nugget diameter that increases the mechanical strength. And then we have a reduction of the shear tension strength due to the fact that in these samples metal expansion occurs, and so we have a loss of the mechanical strength. If you look at this picture, you can denote which is the trend of sublet energy obtained during the test, and you can see that we have more or less the similar trend of the shear tension strength values. Also in this case, the fact of the metal expansions defines a loss of absorbent energy in these samples. Here you can see the two typical fractures that were encountered in this weld component. In particular, we found two typical fractures, bottom two fracture and pressure fracture that you can see here. Both the fractures were ductile fracture. You can see the formation of additional dimples in both the fractures. And here you can see the typology of fracture encountered in the several replications according to the several tests. In particular, you can see that the fractures occurred only in the first samples. This is due to the fact that the pressure fracture was promoted by small nugget diameter. And then we have some several buttonhole fracture that occurred either the trip side or the quenching partition side. In particular, you can see that in this test, in this other test, this test, we have that the fracture was characterized by the fact that the bottom board cord on the flap side, and then we can consider that all in this case we have all the fractures occurring in quenching proportion, the bottom board occurring in quenching proportion steel. At the moment it is not clear if there is a correlation between the side of the bottom board and the test. So there are some conclusions, but you can have a look. In particular, here you can see which is the factor of welding current, the welding time, and the mechanical strength. Obviously, increasing this value, you can increase the mechanical strength. You can see that the mechanical function reduces significantly the mechanical resistance of the welded joints. You can also consider that we have some interfracture fracture and bottom fracture according to the side of the bottom board, the bottom on the ragged side, and according to the process parameters. At the end, we can say that even if we have also a mechanical function, overall we have acceptable shear tension strength for all the samples that are investigated in this study.